Hello, welcome to Convergent Dialogues. This is Xavier Bonilla. On this episode, I am talking with Alex Schnell. Alex does research at the Department of Psychology at the University of Cambridge. She has a PhD in behavioral ecology and currently does most of her work in comparative psychology. We start this conversation talking about comparative psychology, what that means, what it is, what it looks like, and then we talk about her work with cephalopods, more specifically with cuttlefish. We talk about the evolutionary basics of cephalopods and some of the similarities and differences between them. We talk about her work and looking at the mating strategies of cuttlefish, such as male fighting and female receptivity. We talk about the implications of the behaviors of cuttlefish for intelligence and cognition. And then we talk about her more recent research that has come out, namely the study published on cuttlefish passing the Marshmallow Test and why that's a big deal, the importance of delayed gratification and self-control, and what that could mean for other species. As we see other, many birds and chimpanzees and now cephalopods that are able to do this, what does that mean for cognition overall for vertebrates and invertebrates? And we talk about consciousness in animal minds and the implications of studying intelligence in other animals and many, many other topics. I have to say it was a real honor and an absolute blast talking with Alex. She's quite lovely, super brilliant, really knows her research well, and I certainly learned a lot about my favorite sea animal, the octopus and the cuttlefish and all cephalopods. And so it's quite illuminating, and what that means for all animals and us as humans, and how we understand intelligence and cognition and consciousness. And so I'm very pleased to bring you Alex Schnell. I'm here with Alex Schnell. Alex, thank you so much for coming on.
No problem. Thanks for having me, Xavier.
Yeah. So I'll just lay my cards out on the front here. Mm-hmm. The octopus is one of my favorite animals in the ocean, and all things cephalopods. I think they're fascinating animals. Mm-hmm. And I've read your research for a little bit, and so follow you online. And so I'm just really, really excited to talk about one of my favorite creatures for various reasons, and get all of your insights and thoughts and your research that you do with these awesome animals. So just briefly tell us who you are, what your background is in, and what you're currently studying.
So I am a research associate at the University of Cambridge in the Department of Psychology. I have a background in marine biology, and then I went into animal communication, and I was studying how cephalopods change colour and communicate with each other visually. And then I started to get interested in the decision-making processes that underpinned their behaviours, which is how I then moved more into comparative psychology. And now I'm interested in decision-making, learning, and memory in these large brain mollusks.
Mm-hmm. Yeah. And just for listeners' sake, how would you understand or explain kind of comparative psychology? That might be a strange thing for some folks.
Essentially, comparative psychologists, we investigate the different cognitive abilities of animals with the overarching interest in the evolution of intelligence. So that's kind of the broad question that we're interested in. And then we look at different taxa or different animals and try and compare similarities and differences in terms of their cognitive abilities. Mm-hmm. And that helps us that helps us locate the origins of intelligence by looking at quite different animals.
Mm. So it's kind of like this interesting branch of ethology that mixes and merges with evolutionary psychology of sorts, yeah?
Mm-hmm. Yeah, exactly.
Yeah, mm-hmm. Great. That's great. Okay, so let's do a kind of an overview first, and we can talk about some of your research. So maybe just give us a primer for those of us that aren't well versed on marine biology. kind of where cephalopods in general sit, and maybe kind of their, I mean, not do a whole history, but kind of where they sit in terms of who's the common ancestor and how we go all the way up the tree, and then where they sit currently in terms of the categorization.
So cephalopods, they belong to the second largest animal phylum in the animal kingdom, which is called the mollusks. And when I say the word mollusk, a lot of people might think of a slug or a mussel or a garden snail, but it's also home to a group of animals called the cephalopods, which include squid, cuttlefish, and octopuses. It also includes the nautilus, which kind of looks like an octopus encased in a shell. But the cephalopods that I'm really interested in are the shellless ones, which are the squid, cuttlefish, and octopus. So they've lost their shell through evolutionary time. And in that time, they also grew a pretty big brain compared to their body ratio. So they're separated from vertebrates because they're part of an invertebrate group. They don't have a backbone, and they branched off from vertebrates more than 550 million years ago. Their common ancestor with vertebrates would look something like a flatworm with a pretty simple nervous system. And so a lot of the attributes or characteristics that we see in cephalopods that might be compared to what we see in vertebrates are thought to have evolved through a process called convergent evolution, which is when animals, when traits have evolved independently and they weren't found in the common ancestor. And that's because the common ancestor that I described is pretty simple, and it's highly unlikely that that common ancestor would have had, the learning and memory abilities that we see in modern day cephalopods.
Sure. And so there is this kind of split between vertebrates and invertebrates. And that's where we kind of see where some animals, have that backbone, the spinal cord, et cetera. But then there's other animals that obviously have a nervous system, but it's not centralized.
That's right.
Yeah. And so maybe tell us again, or I guess the differences between, so you mentioned the nautilus, is that correct?
The nautilus, yeah.
Yeah. So they have the shell. Is that kind of like an evolutionary vestige that they just kind of have held, or it's just...
Yeah, so they kept the shell. And then the other cephalopods, they internalize their shell. So you'll find a tiny little structure within them. The cuttlefish probably has the largest internalized shell, which is the cuttle bone made of different chambers, which helps the animal stay buoyant in the water column. They're quite different if you look at their characteristics. So the octopus is kind of just a head and with 8 arms attached to it. It doesn't really have a really distinct, the head is just directly attached to the arms.
Yeah.
Whereas it's a bit of a blob. Whereas the cuttlefish and squid have more of a head, body kind of outline. The cuttlefish always reminds me of a rounder version of the squid. And they have a really cute little fin around their body, which looks like a little skirt. And the arms are attached directly to the head, same as squid.
Yeah, I was going to ask you, so you're kind of describing the physical differences, but as we get closer, so you have these 4 animals that are part of the cephalopod group. What are some of the kind of distinctions or things that make them different? So maybe physiological differences are there, obviously, but are there other things that kind of separate them out? Because most people would probably look to them and say, oh, same family or this kind of the same animal. It'd be very hard for people to not really tell a difference. So what would you say are the differences, I guess?
Well, I guess if we're thinking about brains, for example, they have similar brains. They're donut shaped, but they're made up of a different number of lobes. Also, in terms of the size of the brain, so the nautilus has a much smaller brain to body size ratio compared to the squid, cuttlefish, and octopus. And so it's thought that perhaps this brain enlargement was triggered by the loss of the shell. So the soft-bodied cephalopods, they lost their shell and became exposed to everything in the ocean that would eat them.
Mm-hmm.
So they grew a bigger brain to body size ratio. In terms of body outline and physiology, there are a lot of similarities, but again, there's differences. Comparing an octopus to a cuttlefish would be similar to comparing a human to a cat. So in terms of evolutionary time. But I think that a lot of people have a look, see a cuttlefish and they're like, oh yeah, it has 8 arms. It's like an octopus. The one difference, I guess, between squid and cuttlefish and octopus is that the octopus has 8 arms. Cuttlefish and squid have 8 arms, but they also have 2 feeding tentacles that shoot out when they capture their food. So they are different, especially when you're the one studying them. But to people who aren't that familiar with them, they're just like, oh yeah, it's a squishy thing without a shell.
With a bunch of tentacles, a bunch of arms.
Exactly.
Right. So I guess going a little bit further then getting into the behavioral types of things, now you've done a lot of work with cuttlefish. That's not all you do work with. You do work with octopuses as well, correct?
I have in the past, but I mainly work with cuttlefish now.
Yeah. So in terms of a lot of your research is centered around the mating strategies, cognitive strategies, some of the behaviors that we see with cuttlefish. I guess before we get into the specifics, what kind of got you interested in cuttlefish in particular, where you settle?
Well, I think like a lot of people who are interested in cephalopods, I first became fascinated in octopuses. They were just so mesmerizing and very alien-like. So I first began, when I kind of delved into cephalopod research, started with octopuses. And then after working with them for one small project, I switched because octopuses are quite difficult to work with. They are quite finicky. They're difficult to house because it doesn't matter how secure you make the aquarium, they somehow escape. And they have quite stark differences amongst individuals, which means some individuals might be amenable to the type of experiments you conduct. They're willing to participate with whatever you put in the tank, whereas others, just no way. So it's just, I then switched to the cuttlefish cousin, and I just found them a lot more amenable to testing in that they're quite curious, at least the species that I work with. It's different from species to species. They're not overly shy, so whatever you put in the tank, they want to interact with. They're easier to catch than an octopus. So that's why I think I ended up choosing cuttlefish as the more amenable candidates for some of my experiments. And I started with mating strategies mainly because I was really interested in the type of behaviours that were being reported that were coming out of a really large mating aggregation of giant Australian cuttlefish. So one of the largest known aggregations occurs in South Australia. And there were some pretty incredible behaviours which were probably driven by intense mating pressure, because at this aggregation, it averages 4 males to 1 female. And can range all the way up to 11 males to 1 female, which means the competition for these female cuttlefish gets pretty high. And you see some behaviours which are kind of jaw-dropping at first. So the males are very different in size, even at maturity. You have really large males who they fight and defend their females, and they can kind of get in there through muscle power. But then you have a lot of smaller males, which are maybe half the size of the larger males, and they wouldn't have a chance defending females against the larger males. So they change the colour of their skin and they change the posture of their arms to mimic female cuttlefish, and they kind of hoodwink the larger defending males and sneak in there and steal their females. So those are the behaviours that were being reported coming out of this segregation, and what really intrigued me about their behaviours and mating strategies. And I ended up going down that path for my PhD work, looking into female receptivity to see how females chose the male, if they had a say, or was it all kind of driven by male behaviours. And then also I was really interested in male fighting behaviour and what were the characteristics that made it more likely for a male to win a fight.
Yeah, I think in one of the papers you were describing how there's like this white band that goes around the female cuttlefish to basically say, like, you know, kind of give the okay sign. Is that correct? And that it's okay? Is that how that's right?
The other way around. So
the other way around, sorry.
When she flashes the white stripe, it means back off. I'm not interested.
Right.
Yeah. And the interesting thing is that you see some of the small males who are mimicking females do the same, because their disguise, their female mimicry disguise, is so successful. Some of the larger males will sometimes mistake these female mimics for females and will go after them as well. But then, you'll see the little guys flash a white stripe down the side of their body as if to say, I'm not receptive, back off.
I have one other question about that, but in terms of the receptivity piece of it, so there's a lot of, it's a numbers game, right? If there's only one female for mating and there's, 10 males, they're all competing. So it can get aggressive, and, there's a size thing here as well. But what do you think is I think you talk also about that. What is this, something about the right eye and the left eye, and how they're able to, like, different sides of their bodies and all these ways of which are basically saying for their dimensions of how their bodies are, if you will, they're using certain strategies and how they're trying to, get a female mating partner, and what they're doing to fend off others. Maybe talk a little bit about that aspect of it as well.
So, I found through some of my PhD work that the biggest characteristic of whether an individual male would win a fight or not was definitely, the first thing was size, which makes sense as to why the smaller males would then develop or emerge. You'd find these female mimicry strategies in the smaller males, because if size is the thing that's going to win a fight, then they don't have a chance. Then I've also found that because in some of their displays, they have, 3 different displays that vary in aggression. So they'll have one display that kind of means I'm checking you out. I'm not too sure about you. Another display that heightens the aggression, that says, if you come any closer, it's game on. And then another display where they turn their body laterally and kind of like expand their body size. And they also change a color pattern on their body called the passing cloud, which just looks like dark and white bands that pass over their body. So there's also hidden messages within those changing color patterns. So the more higher the contrast is between those dark and light bands, the more likely they are to escalate the fight. So there's lots of different attributes that I think help them or help the individuals communicate their intention and motivation. And it not only has to do with size, but also, the color of their patterns. And then the lateralization stuff came a little bit later. So that was more to do with, you find animals throughout the animal kingdom have these lateralized behaviors. And when I say that, it's just a lateralized behavior in the human population is that whether you're right-handed or left-handed, whether you used one side of your body more than the other. We also, when we talk about lateralization, we talk about brain lateralization, where the vertebrate brain has two distinct, very clear hemispheres, and one side of the brain might dominate in certain tasks, and the other side of the brain might dominate in a different set of cognitive tasks. So in some animals, we wanted to kind of see if this occurred in cuttlefish as well, but in some animals it had been suggested that behaviors that require a little bit, I wouldn't say cooperation, because sex is not always cooperative, but it requires a little bit of alignment and, for it to work, then it's said that the majority of that population is going to be lateralized in a certain way, because for that behavior to persist in the population, then animals have to be have to use, say, so for example, I think in the cuttlefish paper we found that, and you find this a lot in animals, the population, more of them are lefties than righties. Mm-hmm. And when I'm talking about cuttlefish being lefties and righties, I'm not talking about whether they're left-handed or right-handed. I'm talking about whether they lead with their right eye or left eye. Right. And so I think we found that maybe 80% were, lateralized in one way, one direction, and the remaining were lateralized in the opposite direction. And the individuals that were lateralized in the direction that comprises the majority of the population were the ones that were more successful in behaviors that required alignment, like mating. Mm-hmm. So it's like, these individuals are aligned this way, and in order to mate, you need to be aligned in the same direction. And so that helped that particular behavior. Mm-hmm. Behaviors that didn't require kind of cooperation or alignment, or coordination is probably the term that I'm trying to think of, any type of coordination, mutual coordination, then the individuals that were aligned with the minority of the population were the ones that kind of succeeded in those behaviors. So a good analogy here would be boxing. So in sport, left-handers are actually the more likely to win a boxing match than right-handers. Mm-hmm. And that's because they might use a left hook or throw a punch that's less predictable than what a right-hander might be expecting. So they come out of nowhere and they get punched using a behavior that they're not predicting, and so they come out on top in the fight.
Another analogy might be tennis. If you have a lefty that serves, that's a whole different look in terms of spin and how the ball is coming towards you than a righty, probably because of most people are right-handed. So you're used to getting the serve this particular way, but then you get a lefty, there's less of them. There's a lot of spin that's generated. And so it's a new look, and you typically have like with boxing, there's more of an advantage just for the sake of being left-handed.
Exactly. And so that's what we actually found in the cuttlefish. The cuttlefish, now to make it a little bit more complicated, the cuttlefish that led with their right eye were the minority. So they were like the left-handers. But they were the ones that were more likely to win fights. And maybe that was because, they were at more of an advantage because they were using behaviors that were more unexpected. Mm-hmm. Mm-hmm.
Now, you have a mix, I think, in your research of looking at cuttlefish mostly in, what do we call it, live environments, and then in laboratory environments, right? So you have some in both, wild. Right? Mm-hmm. Yeah, wild, yeah, excuse me. Yeah. What are the major, overall, I mean, I'm sure with each study it's different, but overall, what do you find are the major differences between, wild experiments, if you will, and then those in the laboratory, if any?
There's definitely less control in the wild. And that's why I think I started off with a combination of field and lab-based experiments when I was looking at mating strategies, because I think it's really important to have a look at how mating strategies carry out in the wild. And behavioral observations that are taken in the field usually are the inspiration that you draw from to think, I'm going to study this in a controlled environment in the lab to figure out why this behavior is occurring, or what environmental aspects of this particular environment are pushing that behavior to occur. when I then moved more to cognition in cephalopods, I still very much get inspired from, behavioral observations that you might see, but the experiments that we're particularly interested in, where we really want to underpin the cognitive ability that might be driving a behavior. Mm-hmm. The best environment to do that in is a lab environment, because you need to control for a lot of other explanations. Because when you're seeing a behavior at the superficial level, you might think, wow, that's incredible. That looks super sophisticated, and this animal must be really intelligent to be able to carry out this type of behavior. But the brain, if the brain can take a cognitive shortcut, it will. And so even though the behavior might appear to be really sophisticated, it doesn't mean that the cognition that's driving that behavior is also sophisticated. Mm-hmm. It might be something more simple, such as associative learning, where an animal has learnt a particular pattern and just applies that rule to every situation. So that's kind of the crux of what comparative psychologists are trying to do when we try and identify the cognitive ability that's driving this behavior. We need to control for any type of explanation, so that we don't say, yeah, it's definitely this type of complex ability, without ruling out more simpler explanations.
Certainly. Yeah, that's nice. One thing before we move to the cognitive strategies, I guess in kind of a, I don't want to say conclusive, right, but in a discussion way, this is pretty incredible. I mean, maybe it's incredible for us as humans because we can't do that. But this idea of, okay, I'm a smaller male and I'm going to change my patterns and my color and, different designs and all of these things on the body to really trick, other males. There's a certain amount of, if you want to call it, intelligence. There's a cognitive ability there, right? There's something there that, I think if you were to take any set of animals, they have their own ways of trying to adapt, right? And try to work, with advantages against them. But I guess just as again, not a definitive thing, but, what can we say in an applied sense of, what does that mean and how we understand cognition, or anything else with cuttlefish and how they're able to do that? I mean, that's definitely, at least for us, remarkable. But what do you think about it?
So we're still very much at the beginning of understanding the cognition that's driving these color changing or pattern changing abilities in cephalopods. So they not only have the ability to camouflage, which means they can match their skin to blend in with their background, but they can also mimic, which is mimicking other animals, whether it's an animal of the opposite sex or a completely different type of animal, or they can masquerade, which is what we call a cephalopod that isn't mimicking another animal, but it's disguising itself as an inanimate object, whether it's a rock or, it's not disguising itself as another animal. So it's pretty fascinating, because more recent research has shown that these type of behaviors aren't ingrained within the animal's genetic makeup, meaning that it's not hardwired. It's not something that the animal just hatches out of an egg and can do it straight away, kind of like the way that birds migrate. That's a hardwired behavior.
Sure.
Whereas there is some learning associated with camouflage, mimicry, and masquerade. That's as far as we've gone. We don't know whether there's any other complex cognitive abilities that drive these behaviors. It's possible, because I think one of the really interesting questions that could be answered within the context of mimicry or masquerade is that the animal might have some sort of ability to distinguish its own self from the self of other individuals or other objects in their environment. And I'm talking about a field of research that is called theory of mind, which is still a very contentious field even within
humans, it is.
But within humans, right. But it's still interesting to think, well, if an animal such as an octopus can take on, disguise itself as a moving rock because there might be a barracuda in the ocean watching it, what kind of abilities are driving this behavior? Does it mean that it has the ability to distinguish its own perspective from the barracuda's perspective, and also to distinguish that it is taking on a different form to disguise itself as an anti-predatory strategy? Of course, there are simpler explanations for this type of thing, that it might have learnt simply that disguise myself as a rock and I won't get eaten, and it doesn't have to think about, distinguishing its own mind from the mind of whatever it is disguising itself as. But it's still an interesting avenue of research that could definitely be explored because of the behaviours that we're seeing in the field. And that's why, you see these behaviours and you're like, oh, that would be interesting to test in this particular context of psychology, because at a superficial level, it could be possible that it could be driven by these complex abilities that we've only kind of seen a little bit of evidence for in chimpanzees or crows in humans. Could it be possible that an octopus has evolved this type of ability too?
Well, I guess my one piece on that is that there's something about, I think the big question here is intention. Are they intending to do something, regardless of if there's a threat, right? Or a mating type of strategy there, but there's an intent. The $64,000 question is, are they intending to do that? Which would take some aspect of metacognition as well, because then it's like, if you have the capacity to switch colors and to switch patterns, is it something that the animal knows it can do? And if it knows it can do that, but there's some awareness of their body, quote unquote body, and their what they're able to do and not do, to then, yes, have the associative learning to say, oh, every time I do this, this happens. This other animal doesn't have, can't figure this out, or they don't have the capacity to figure it out. And so the question is, how much are they knowing what they're doing when they're doing it? Or is it just a kind of, I don't want to say random, but it's just just purely an associative learning thing? Because I think you could make the argument that, behavior doesn't sit in isolation, right? You could argue that there are things driving behavior, right? There's always things driving behavior. You can learn it and you might not be consciously thinking about it in the moment, but then it's like, okay, well, how? Obviously we don't know, right? That's why, people like yourself keep doing research, but that idea, and we don't know intention even in humans, right? So this is hard stuff, but are they aware that they're doing it? And are they aware that they're doing it so they don't get eaten, or so they can have the better mate, or so? That's I guess the big question still. Yeah. But yeah. Okay. Okay. So let's do the cognitive strategy. So I'm sure you were very excited when various people were, tossing and passing and reposting around your recent paper with the Marshmallow Test, or a variant, I should say, of the Marshmallow Test. So maybe just give us the snapshot of what the Marshmallow Test is, and then how it works, and then your variant of it, and then why it's a big deal, why everyone was getting all excited about this.
Yeah, sure. So the Marshmallow Test was developed in the late 1960s to early 1970s by psychologists who were interested in investigating the willpower of toddlers aged between 3 and 5. And so specifically, a child would be led into a room and presented with a single marshmallow and told that they were allowed to eat it, but if they didn't eat it and were able to wait 15 minutes, they would then be rewarded with 2 marshmallows. And so we adapted this marshmallow test. We had a similar setup, but rather than offering cuttlefish marshmallows, we offered them different kinds of shrimp. And so we found we first found the individual food preferences of each cuttlefish, and we used their first preference as the biggest reward or the best reward, and their second preference as a reward that they could eat straight away. But if they were unable to exert self-control, then, or if they were able to exert self-control, then they'd be given the better reward. Now, obviously, we can't tell a cuttlefish to wait, like the psychologist did in the original Stanford Marshmallow Test, which is, so we kind of have to think outside the box, and we have to come up with behavioural kind of criteria or indicators to test whether the cuttlefish has understood the aim of the task. So initially what we did is we trained cuttlefish to learn that different chambers that could be placed in their aquarium tank, clear chambers, offered prey that had different accessibility. So one chamber that we would place in their tank, and it was marked with the visual cue. Cuttlefish are really visual, and they can distinguish between different visual cues. So this particular chamber, when we put the food inside, the door would open straight away. So we trained them to learn that there was an immediately available chamber, and then the other chamber that we would insert into their tank had a delay. So once the food was inserted into the chamber, the cuttlefish could see that the food was in there. The door wouldn't open for a few. So we started at a few seconds, and then we increased that. And so we trained them to learn differences in those chambers. And then once they were showing very distinct behaviours towards those chambers, and by that I mean the minute the immediate chamber would be inserted into the tank, the cuttlefish would swim straight up knowing that that door was about to open. Whereas the delay chamber, they would always hold back and kind of wait until that door would open. So once we saw those clear behaviours in response to those different chambers, we tested them using two chambers and giving them a choice to choose or to swim up to the chamber that was immediately opened or the chamber that was delayed. And the immediately available chamber was always baited with their second preference, and their delayed chamber was always baited with their first preference. So they had to choose whether to swim up to the immediate chamber that had, a second preference that, say, might be, I don't know, a cookie, but, or they would hold out and wait until the chamber that had their first preference, say that might be chocolate for a toddler. And what we did find is that all cuttlefish had the ability to delay gratification and actually hold out for that better reward. The maximum wait time that they showed did vary across individuals. So the cuttlefish...
What was the longest wait time?
So the longest wait time was 130 seconds, so just over 2 minutes, and the shortest was 50 seconds.
That's pretty good. It's a pretty good interval.
Yeah, pretty good for a little cuttlefish. So we were kind of expecting, resisting temptation for a lot less. So self-control isn't something that we just see in these large brain kind of animals.
Sure.
Self-control has been tested in a lot of different animals. But it just depends on the ability to resist that temptation. So and that tolerance for temptation really varies across taxa. So for instance, animals like rats, chickens and pigeons, they find it really difficult to resist temptation, and they have relatively lower levels of self-control. They'll only wait several seconds for a better prey item, whereas animals such as chimpanzees, crows, parrots, they show more of this advanced self-control and can wait up for several minutes for food of better quality or quantity. And so our cuttlefish showed these comparable levels of self-control to this latter group of animals, the chimpanzees and the large brain birds. And I think that's what was really surprising in our findings.
Yeah, I mean, I think of all the behaviorism stuff, the Pavlov's dogs and Thorndike's cats, and I think what was the other one, the pigeons, and self or delay of gratification is not something that is novel necessarily, but I think what you're saying is right. I mean, we've seen it in rats, we've seen it in other birds, but it's more of the time, right? Because you could, again, I would imagine, postulate that they have to, in some ways, there's the delaying gratification, but there's also the how does it consolidate in memory, right? At least in short-term memory, right? And how long can that go for saying, okay, I can hold this in short-term memory to know, oh yeah, this opens up, and then I'm going to get how long can that go? Again, you could say that there's just with time, you can make I would imagine, a good inference of, okay, there's a certain level of brain power there, right? If, other animals can only hold it for 15 seconds. All right, that's pretty good. But if you can do it for over 2 minutes, I mean, that's damn good, right? And humans can do it for, it depends on the human, I guess, but right. They can delay gratification for some things, for a while. But you start to make, again, ideas about what it could say for kind of brain power. But okay, so there's the delayed gratification. There's a certain amount of time. But what else can you say, I guess, honestly or fairly to the results that you feel confident to say? Is there the memory piece? Is there somewhat of a sort of executive functioning piece of how they're kind of sequencing things, or is that too far of a jump?
It's too far of a jump at this point, but I guess what we also found that was quite interesting is that, so in humans, and it's also been shown in chimpanzees, that the ability to exert self-control has been linked to cognitive performance in other tasks. So in humans, individuals that can perform better in a range of different academic tasks exert greater self-control. And then a paper that came out in 2018 showed a similar pattern in chimpanzees. And so we wanted to see whether this was also true in our cuttlefish, because they had that variable maximum wait time. We wanted to see whether the individual that could wait the largest amount maybe had better performance in a different task. So we zoned in and we just looked at learning performance in a separate reversal learning task. And we did find a correlation between the two different traits. The individuals that waited the longest were the fastest learners in the other task. And so it's just a correlation. And we had a small sample size, but it's interesting to find this similar link between these two different traits, and it makes you, I guess, as science always does, it raises more questions as to whether how strong that link is cognitive performance or intelligence in other tasks really important for self-control, or does good self-control, is that fundamental for intelligence? So that was another interesting pattern that we found. Overall, I think in terms of the importance of the study and why, I think it went viral because a lot of people know what the Marshmallow Test is. A lot of people have conducted the Marshmallow Test on their own children. And here is a cuttlefish, this bizarre mollusk-like creature that has passed the Marshmallow Test. But I found it super interesting, I guess, because it updates our understanding of the evolution of intelligence, and specifically why and how self-control evolved. So our current understanding has been very much based on evolutionary pressures that are relevant to long-lived and social species, such as brainy birds, including crows and parrots and apes. And the benefits for self-control are obvious for these animals. Because animals that live a long time and are social might resist temptation in the present to obtain better outcomes in the future, and that might help them live a longer life. These groups of animals might also resist eating before their social partner to strengthen social bonds, and that might also help them receive reciprocated favors from their social partner in the future. Self-control might also be a result of tool building. So apes, crows, and parrots, they build and use tools, and they might need to resist the temptation of hunting or foraging in the present moment so that a functional tool can be built to optimize their hunting behavior. Mm-hmm. Now, all these theories on these rules, they don't apply to cuttlefish. You know, they haven't experienced the same pressures. And so finding self-control in cuttlefish might be a really extreme example of convergent evolution, because the cuttlefish mm-hmm. has significantly different evolutionary histories from the more commonly studied long-lived social species. They're short-lived, they're not social, and they don't build tools. Right. So we don't know why it evolved in cuttlefish, but we speculate that maybe it evolved to fine-tune their eating habits. So cuttlefish, they spend the majority of their time camouflaged. They remain motionless to avoid detection by predators. And these long bouts of camouflage are broken when the animal needs to eat. Mm-hmm. And so perhaps they evolved self-control to optimize their hunting excursions. Waiting for better quality or preferred food might speed up their hunting excursions and then limit their exposure to predators.
Yeah, I think the finding of it as well is just showing that, well, you have one thing such as delayed gratification or self-control that for social primates like chimps or bonobos or humans has one implication for a social animal, but for an animal that is not social, it could have other implications, which would mm-hmm. kind of show the hybrid of how that works. Mm-hmm. Which is terribly fascinating. Mm-hmm. So the last bit here that it's kind of hard to end on this because it's really complex and there's a lot of I don't knows and question marks, but I'll be really curious mm-hmm. to hear your thoughts because you work with this is, mm-hmm. Consciousness, right? And animal mm-hmm. minds. And mm-hmm. this is something that many people have been very quickly jumping to, mm-hmm. especially in the octopus. Mm-hmm. Myself, I also have thought, maybe they are kind of, conscious and, mm-hmm. Which is difficult because we don't even know what the hell consciousness is in humans, much less in anyone else. So it's a thing, right? Like, there's something of what it means to be you. There's, the lights are on, whatever. Right. But, how do you, just in general, what are your general ideas or positions about that? Because I think in some of the papers, you do a really honest job, and it's something that's really, really nice that made me think twice was we're trying these observable behaviors in these animals are not necessarily indicative that they are conscious. And I mean, they might be, but we don't know. And also, how does that change kind of what we were talking about with the self-control and delayed gratification? How does that change how we understand cognition in general or intelligence in general and what that could mean for other species? So maybe mm-hmm. talk about the consciousness piece and what you think about that and everything there.
Yeah. So I feel like consciousness, especially in animals, it's often the elephant in the room that no one really wants to talk about. Right. It's enormously controversial. And I think it's probably because most of us aren't even trained to answer that type of question. Like if you look at animal cognition textbooks, consciousness is either a topic that is not mentioned or not given much attention. And so researchers often steer clear. Mm-hmm. But I think it's a pattern that needs to change. Because without guidance on how to move forward in this area of research, comparative psychologists will be excluded from the science of consciousness. And as a result, our science might end up weaker. Yeah. Like I said, it's really controversial. And that's a lot of because we can't verbally communicate with animals. So we can't ask them to describe an experience that might be subjective to them. Now, in terms of cephalopods and consciousness in cephalopods, we have a long way to go before we can really comment on their consciousness. That isn't because to say that they don't have, that attribute, but it's just, I think even cognitive studies, particularly where we look for complex abilities, we're very much at the start of that with cephalopods. I think it might be easier to talk about it in corvids. So they're large brain birds that include crows, ravens, and jays. And, there is extensive research conducted on corvids to show that they kind of parallel chimpanzees when it comes to particular cognitive abilities that might be tied to consciousness. And that particular ability is planning for the future.
Yeah.
So a key element of planning for the future is that an animal must make future provisions when tested in a novel context. So it's not that they've learnt a pattern and they need to plan for the future, because it's not just a pattern or a behavior that they show on demand through associative learning. It has to happen in a novel context. It has to be spontaneous to then provide evidence for this animal has considered that they might be put out if they don't make future provisions in a particular novel context. So, for example, one of the really famous examples of future planning was conducted in scrub jays. So scrub jays, they experienced two different rooms. One room always offered breakfast and another room never contained breakfast. And so they were just exposed to these three different rooms for 3 days at a time. Then they were given an opportunity to cache, so take nuts or different type of kibble from adjoining corridor that joined these rooms, and they were given the chance to store that in either the room that offered breakfast or the room that didn't. And what the individuals did, they spontaneously cached in the room that did not offer breakfast. And so that kind of level of spontaneous planning, where they hadn't been trained to cache in either room before, it was just they'd experienced no breakfast in one room, and then they're like, okay, now we're given the opportunity to cache. I'm going to that non-breakfast room and I'm going to store all these goodies in there just in case I'm locked in there one morning. Right. So that level of spontaneous planning is really a gateway, I think, to consciousness research without the ability to test it verbally. Because I guess I'm going to go out on a limb here. I can't really see how an individual could spontaneously plan for a future event like that without consciously recollecting a past experience.
Well, it would be, it has to have something where there's some delineation between prospective memory, right? Which is this kind of basically what you're saying, but there's a memory component to it of, oh yeah, I remember this time I had to, okay, I should plan for the future. I think that the spontaneity and the novelty of it is the key yardstick there for trying to understand, are the lights on here? Is this just, is what we understand to be consciousness, is that going on? Kind of goes back earlier to what we were saying about the intention. Like, is that intentional? Is there some consciousness there for this sentient being? Or is this more of associative learning, behaviors, memory, et cetera? Which is, but again, without the verbal component, it becomes very hard to do it. Just real quick, so I don't know if you know Franz de Waal, he's done work on this stuff. He talked about, are we smart enough to know animals, right? Because we're always using human instruments to test animals, and it's like, there's always going to be a gap there. It's always going to be something missing. I had recently Mark Solms on the podcast. I don't know if you're familiar with Mark Solms. And so he just came out with a book about a month ago, maybe, about consciousness. And he posits that consciousness originates in the brainstem, namely in the midbrain, and in the PAG, right? It's just the gray area. And so his idea is that it's connected with emotions and affect, and that you find that the work he did with Jean Panksepp and a few others is that this works with vertebrates, but he doesn't know. And you see that all around. Obviously, cephalopods don't have that. So then it becomes this idea of, it could be, it's possible, right? But if you're finding the origins within the midbrain of the brainstem, and then it goes out across the cortex and subcortex, then you would say, well, you would expect to find this in vertebrates. And in some ways, in some research, they have seen traces of that. Okay, that's promising. Octopus don't have that. Cuttlefish don't have that. However, I wonder if, if it does branch out, or you do have this convergent evolution of sorts, it's just a mystery. So I don't know what you think about that piece, or if you've heard that kind of idea or whatever.
I have, and I think it's really, it's fascinating, but it is difficult when we take a characteristic or an attribute that's mainly found in a vertebrate, and it's hard to then bring that across different type of taxa. And even with the example that I just gave before, talking about mental time travel, the ability to re-experience the past and plan for the future, when I'm discussing consciousness within that context, I'm discussing it within a single dimension. And I think the dangerous thing of discussing it within a single dimension is you ignore all the variation that we find in the animal kingdom. So I'm currently involved in some really exciting new theoretical research about animal consciousness, which is it's led by Associate Professor Jonathan Birch at London School of Economics, and in collaboration with my current supervisor, Nikki Clayton. But this theoretical work is a part of Jonathan's project called the Foundation of Animal Sentience. And essentially, the three of us are proposing that in order to move the field forward, we should dispose of the idea that animal consciousness might occur on a single sliding scale in which a species might be ranked more conscious or less conscious, where you're particularly looking at one particular attribute that is going to distinguish whether that animal is conscious. So that type of one-dimensional scale will inevitably neglect dimensions of variation across species. Where we recently published a paper in Trends in Cognitive Science, and we're proposing that we should develop a multi-dimensional framework for understanding interspecies variation in states of consciousness. So we describe 5 different dimensions of consciousness. Some of them, one of them is called evaluative richness, which is what you were talking about before, where a species might be attuned to positive or negative emotions. One of them is also mental time travel. That's one dimension. Another dimension is selfhood. So by that, we're talking about theory of mind, mirror, the mirror self-recognition test. And so I think the important thing is using that multi-dimensional framework might help us identify different types of consciousness dimensions so that we can then develop, I guess, a consciousness profile for a species. So, I'll give you an example. Say we used one particular dimension of consciousness to distinguish whether an animal was conscious or not. And it might be focusing on selfhood or self-consciousness. And so by using this dimension, we might say a chimpanzee might be considered highly conscious because they've passed the mirror self-recognition test. There is some evidence to say that they can distinguish their mental state from the mental state of a different individual. By contrast, if we're talking about a cuttlefish against the dimension of self-consciousness, we might say it's less conscious, or perhaps it's not conscious at all, because they fail to recognize themselves in the mirror. They have really poor recognition skills, and there's no evidence to suggest that they're capable of theory of mind. So this one-dimensional approach then really neglects the fact that cuttlefish might possess different types of dimensions. So they possess really rich perceptual experiences through vision. They process information bilaterally, which means they're capable of unity because they can integrate information from both eyes, and that's one of our dimensions in the paper that we propose. They can also integrate experiences across time to guide their behaviour. So there's evidence of retrospective memory, episodic-like memory, and evidence of planning for predicted, proximate future expectations. So no evidence of future planning yet. But then by applying that multi-dimensional approach, we can highlight these dimensions, and that can lead to really important revelations about cuttlefish sentience without just focusing on one particular dimension that might be really suitable for a chimpanzee, but not for another animal.
And I guess just lastly here is what does that mean as much of evolutionary psychology, or probably better evolutionary science, I guess you could probably better say it that way, is, what does that mean for humans, right? Not for you and I as humans to be so narcissistic, but, from our perspective as our species, right? How do these ways of understanding cognition, intelligence, possibly consciousness, what does that say, or how does that impact how we understand human intelligence, cognition, as also kind of within this kind of constellation of other animals that can do certain types of things. How do you think about it that way and juxtaposing it that way?
I think the more and more we study diverse animal minds, we come to realize that the attributes that we used to claim as being uniquely human are not uniquely human. And that makes sense from an evolutionary perspective. It's not like, okay, humans evolved and with them all these really sophisticated cognitive abilities evolved, and not even prerequisites of that are observed anywhere else in the animal kingdom. That just doesn't make any sense.
Yeah.
So I think, as we're expanding and looking at less traditional model species like the cephalopods, we're starting to see at least, I'm not saying it's the same feature, but at least similar cognitive features that have emerged across the animal kingdom. And that helps us understand, I guess, or locate the origins of these different cognitive abilities that we might be interested in. In terms of what that means for human intelligence, it also answers questions about our own intelligence. Where did it originate? What particular pressures might have driven those intelligent behaviors or cognitive abilities? And could they be driven by slightly different pressures in animals that haven't experienced the same sort of pressures? And I think it depends, because, the question you asked, I guess, integrated a little bit of consciousness and intelligence. But I think an important difference between those particular aspects of cognition in a whole kind of need to be made, especially when we're interpreting results. So when we're investigating complex cognition, whether a particular animal has a theory of mind or future planning or metacognition, we often adopt a very parsimonious view. So without the strong evidence and the experimental controls to ensure that the animal isn't using a simple cognitive shortcut, comparative psychologists are trained to elect the simpler explanation for a cognitive phenomena in favor of the more complex one. And that approach isn't because we're trying to be a killjoy. It rather conserves the uniqueness of complex cognitive abilities and really helps comparative psychologists preserve an authentic understanding of the evolutionary patterns of intelligence. So I think that's why we're always careful to say, this could be a similar cognitive feature, but this could be a simpler, what we're seeing could be explained through this simpler explanation, because we don't want to say, it evolved in this animal, this animal, this animal. Then the foundation of the science on what we're trying to build new science on becomes really difficult to navigate. And our understanding of those evolutionary patterns could be incorrect. Now, the parsimonious view, however, is not really enforced when we're considering animal sentience. And that's particularly in the context of animal pain or suffering. So when we're talking about sentience and negative emotions, we normally adopt a precautionary principle, which is based on the idea that strong evidence shouldn't be required before deeming that a species is sentient, especially when it could lead to whether it's worthy of legal protection. And so in that sense, I think we're a little bit more lenient to be like, okay, the evidence doesn't have to be super strong, but there is evidence that an octopus could feel pain, then that could lead to some pretty incredible changes in terms of animal protection legislation, and also it could curtail unnecessary suffering in animals that might be used for science or in industry. So they're the kind of two different approaches when we tackle those different aspects of cognition.
And it could feel physical pain, but it could be potential that it could feel emotional pain as well, which is another dimension to throw it in there for you.
Exactly. And there's some really interesting research coming out of the Crook Lab, actually, in San Francisco. She just brought out a paper in iScience showing that there is evidence of the octopus feeling the affective component of pain. So she uses a framework to test that's used in mammals to test whether mammals are able to experience the emotional side of pain, and her results are pretty compelling.
That's yeah. I'll definitely have to read the paper. It's very fascinating, and again, it's this ever evolving way of understanding different animals and the convergence that's there across species. It's very fascinating. Well, Alex, I want to be respectful of your time. You've been very generous.
I could
Please,
talk all day.
I know. Yes, me as well. Me as well. So please tell listeners where they can find your research, where they can find you online, or anywhere that is kind of applied for you that you would want to give out.
Sure. I do have a website that needs a lot of updating. So rather than visiting the website, probably to my Twitter account, which would be most up to date. I'm at Dr._Alex Schnell on Twitter.
Okay. Well, Alex, again, you're very lovely. You're extremely brilliant. I love all your research. I've read a lot of your stuff, and it's really a big honor to, talk with you about one of my favorite animals and the whole idea of intelligence and consciousness. It's all riveting stuff. So I can't say thanks enough.
Thanks so much for being interested.
Of course. Thank you.